In the skies above, fighter jets roar with incredible speed and power, defending nations and shaping the future of warfare. But have you ever wondered how these marvels of technology come to life? What does it take to build a machine capable of flying faster than sound, evading radar, and delivering precision strikes? Today, we were taking you behind the scenes, inside one of the world's most advanced aerospace factories, to reveal the complete journey of a fighter jet. From the first pencil sketch to the final test flight, witness the extraordinary craftsmanship, cutting-edge technology, and relentless dedication that transform raw materials into a supersonic warplane. This magnificent machine is the pinnacle of human engineering, a modern fighter jet capable of speeds over Mach 2, carrying advanced weapons and defending nations. But how is such a complex aircraft made? Join us on a journey through the entire manufacturing process, from initial concept to a combat-ready fighter. It all starts at a cutting-edge aerospace factory sprawling over several square kilometers. Behind secure gates, thousands of skilled engineers and technicians work together. Before any metal is cut, years of research and design happen in a modern engineering center. The design phase alone can take 5 to 10 years. In conceptual design rooms, engineers and military officials discuss requirements: speed, range, payload, stealth, and mission roles like air superiority or reconnaissance. Every detail is analyzed carefully. Initial ideas begin as sketches exploring wing shapes, tail designs, and engine placements. Most concepts are discarded, but promising ones move to advanced 3D computer modeling, where every curve and internal component is precisely defined. Aerodynamics are critical. Using computational fluid dynamics, engineers simulate airflow at various speeds, adjusting shapes to reduce drag and improve lift. Thousands of simulations help optimize performance. Stealth design is equally important. Surfaces are shaped to deflect radar waves, and even small details like panel edges and antenna placements are refined to reduce detectability. Structural designers create the internal skeleton, ribs, spars, and bulkheads that must withstand forces up to 9 times gravity during combat maneuvers. Systems integration teams plan the complex routing of fuel lines, hydraulics, wiring, and avionics, ensuring everything fits without conflict. To validate designs, precise scale models are built and tested in wind tunnels, where airflow and stability are measured at speeds over 2,000 km/h. Data from these tests refine the design further. Throughout, design reviews bring engineers, managers, and military clients together to solve problems and approve changes. After years of iteration, the prototype design is finalized, existing fully in digital form. Building the jet requires extraordinary materials. High-strength aluminum alloys form lightweight structures. Titanium is used in hot, stressed areas. Carbon fiber composites provide strength with minimal weight, and special steels are reserved for the toughest parts. Molten aluminum is alloyed and cast into large ingots, cooled carefully to avoid defects. Titanium is processed in vacuum furnaces and forged under immense pressure to align its grain structure for strength. Carbon fiber production begins with precursor fibers heated in oxygen-free ovens, transforming into strong, lightweight carbon strands. These fibers are woven into fabrics with different patterns tailored for specific strength needs. The fabric is impregnated with resin to create prepreg sheets, which are stored frozen until used. Specialty steels are melted and tested for landing gear and critical components, with every batch certified and traceable. Component manufacturing takes place in vast machine shops filled with advanced CNC machines. Programmers create precise cutting instructions from 3D models. Massive 5-axis machines carve complex fuselage frames, spars, and bulkheads from solid blocks, removing up to 90% of the material. Bulkheads are machined with lightning holes to reduce weight, and wing spars are crafted from single pieces for maximum strength. In clean composite layup rooms, technicians place prepreg sheets onto molds, controlling fiber orientation layer by layer. Parts are cured in autoclaves under heat and pressure, bonding layers into solid structures. Non-destructive ultrasonic inspections detect any internal defects before parts proceed. Landing gear components forged from special steels are machined to exacting tolerances, ensuring smooth operation under extreme loads. Polycarbonate sheets are heated and formed into canopies, which are coated with protective and radar-absorbing layers, often giving a golden tint on stealth fighters. Control surfaces use lightweight honeycomb cores sandwiched between metal or composite skins for stiffness and low weight. Internal fuel tanks are welded with baffles to prevent fuel slosh and leak tested thoroughly. Hydraulic components are precision machined and tested under high pressure, while miles of wiring harnesses are built and tested for perfect connectivity. The jet engine, the fighter's heart, is built in a dedicated factory. Turbine blades are cast as single crystals with internal cooling passages, machined with laser-drilled holes, and coated with thermal barriers. Compressor and turbine discs are forged and machined for perfect balance. Engine casings, combustors, and afterburners are assembled with thousands of cooling holes to withstand extreme temperatures. Engine assembly occurs in ultra-clean rooms, where technicians carefully build and balance rotor assemblies and mate major modules. Engines are tested in soundproof cells, running through full power and afterburner tests, with engineers monitoring hundreds of parameters. Avionics are manufactured in high-tech facilities. AESA radars are assembled from thousands of tiny modules, tested for precision and reliability. Radar systems are integrated with processors and cooling systems. Cockpit displays, head-up displays, and helmet-mounted sights are built and calibrated to provide pilots with critical information seamlessly. Flight computers control the fly-by-wire system with multiple redundancies, while inertial navigation systems use precise gyroscopes for accurate positioning. Electronic warfare systems detect and jam enemy radars, and secure communication suites keep the fighter connected worldwide. Weapons integration ensures missiles, bombs, and guns interface perfectly with aircraft systems. Major airframe assembly begins with the forward, center, and aft fuselage sections built on precision jigs. The cockpit is outfitted with controls, instruments, and the ejection seat, all installed with exacting precision. The center fuselage houses engine bays, fuel tanks, and wing attachments, while the aft fuselage includes heat-resistant structures and tail attachments. Fuselage sections are joined using laser alignment and thousands of fasteners, forming a continuous structure. Wings are assembled separately, with spars, ribs, fuel tanks, and control surfaces installed. Wing skins are bonded and riveted, and the completed wings are attached to the fuselage with massive pins designed to carry heavy loads. Systems installation follows. Hydraulic lines, pumps, actuators, fuel systems, electrical wiring, environmental controls, and avionics are all connected and tested. The engine is lowered into the bay and precisely aligned, with all fuel, hydraulic, and electrical connections made. Landing gear assemblies, wheels, brakes, and doors are installed, and the canopy is mounted and sealed. The aircraft moves to painting, where surfaces are primed and coated with corrosion protection and radar-absorbent materials for stealth. Final paint schemes and markings are applied, including national insignia, unit badges, and technical stencils. The nearly complete fighter is weighed and balanced to ensure the center of gravity meets strict limits. This data is recorded in the aircraft's permanent documentation. Ground testing begins with comprehensive system checks, automated sequences, and manual verifications. Any faults are corrected before engine ground runs, where the engine is started and run through all power settings, including afterburner tests. Taxi tests verify ground handling, brakes, steering, and engine response. Pilots assess cockpit visibility and control feel, making adjustments as needed. The first flight is a major milestone. Flight test engineers brief the pilot on maneuvers and safety procedures. The pilot inspects the aircraft, starts the engine, and taxis to the runway. After clearance, the fighter accelerates, lifts off, and climbs smoothly. Chase planes observe, and telemetry streams data to engineers. The pilot evaluates handling, systems, and performance during the flight. After landing, the aircraft is inspected, and data is analyzed. The flight test program expands to cover the full operational envelope, including weapons testing and carrier operations. Once all requirements are met, production aircraft undergo customer acceptance. Military officials inspect, review documentation, and conduct acceptance flights. After successful evaluation, the aircraft is formally handed over. The completed fighter, bearing its nation's markings, departs the factory for its operational base. There, it joins squadrons, flies missions, and stands ready to defend. This incredible machine is the result of years of work by thousands of dedicated professionals, designers, engineers, machinists, pilots, and technicians, creating one of the most complex and capable aircraft ever built. Thank you for joining us on this journey inside fighter jet manufacturing. If you enjoyed this documentary, please subscribe to Spy Family for more amazing content. Hit the subscribe button and bell icon to stay updated. Until next time, fly high and stay curious.